Hello. In this lesson, we're going to learn about single slit diffraction. This is the high-level extension of the diffraction we learned in the previous lesson. So it's a part of topic 9, wave phenomena. It's lesson 9 of my playlist, waves and oscillations and wave phenomena. First, I'm going to give you a little task. If you have a laser pointer at home, or a device like this, which I happen to have in my house. This is a tool actually used as a spirit level and to see alignment. It has this red line coming out of it when you turn it on, a kind of a laser, and this is the source. And what I did was, with a little piece of paper, I made a little cut. I produced a single slit from making a little cut on a piece of paper and taped it in front of the source. So this is what I did. You can do this with a laser pointer if you have any at home. If not, you can use a flashlight and a dark piece of paper and a little single slit in front of it to try this yourself. I strongly recommend that you do this. So here is what I did with it. I put it on a table, and with this ruler you're going to see how far I'm moving back and forth. I want you to watch what we see on the screen when I turn it on and when I move it forward and backward. So on the wall you see a bright region. As I move it closer to the wall, it gets smaller. But also watch these sides of this central bright region. It's very, very small when it's close. Now I'm moving it back, and you can see kind of an interference pattern over here. You can see there's a central bright region, and then a minimum here, and then a very low intensity maximum, and it goes on. There is a pattern. I really strongly recommend that you try this and see this for yourself. So let's go. You will remember this from the diffraction lesson. I will use the same simulation and show you how the gap size, this is a wall here and a wall here. I'm going to send plane waves from the top. Without changing anything, I'm going to be changing the gap size. I'll make it bigger and bigger. But this time I'd like you to focus on how wide the bright region is over here. Very small gap, and you see a very wide bright region. Now a bigger gap, and you see about that much of a bright region. Even bigger gap. Please observe that this central bright region, as we call it in physics, has gotten smaller. I made the gap bigger, and this section got smaller, and here is the first destructive interference. Here would be the first destructive interference on the other side of the central maximum. Let's make the gap even bigger. So when the gap is even bigger, you can see that this central bright region is almost straight. The gap is now too big compared to the wavelength. This is a similar case of not being able to observe diffraction of light around a large door, for example. That doesn't mean light is not diffracting. It is. All waves have these properties, but the diffraction effects are too small to be observed. So now I have another simulation to show. Here we have the gap size. This is a circular aperture, and this screen shows the image that forms on the screen. So this is a source of currently red light. That's the obstacle with a little circular aperture in the middle, and light spreads, diffracts, forming a central bright region, which is this, on the screen, um, dark region around the central bright, and then the next maximum has much lower intensity than the central bright. So let's see what happens when I change the size of this gap. When I make the slit bigger, you should see that the central bright gets smaller and vice versa. Now let's see what happens when I decrease the wavelength. Please observe that at low wavelength, there is a smaller central bright. At long wavelength, like red right now, there is a larger central bright maximum. So we observed two things. The size of the slit affected the size of the central bright region inversely proportionally, and the wavelength affected the size of the central bright region directly proportionally. This is to summarize what we just saw. So, light, show screen, and then intensity graph. The slit width is at that level, and green light starts approaching the screen. The intensity diagram on the right shows us the intensity form. Now I've increased the slit width, and because I've increased the slit width, the intensity has increased. We can't even see the top of this bell curve here. There is more intensity because there is more space for light. So more of these point sources between the start and end points of the gap really. So there is more light exposure on the screen. So the central bright becomes more intense. However, I want you to also watch the width of this central bright region. When I increase the gap, this width of the central bright actually decreased. Now I'm changing wavelength. When I replace green with red light, what happens to the wavelength? The wavelength increases. Red has a longer wavelength than green. Let's see how that impacts the pattern. Initially, the gap size is the same. Now increasing the slit width, we have more light coming in, so intensity should increase, but watch what happens to the width. You know that blue has the smallest wavelength of these three, and red has the largest wavelength. And you can see with the same slit size, they have about the same intensity. Please observe that as wavelength increases, that point becomes further and further from the midpoint. Let's say these plane wavefronts are approaching an obstacle. In the obstacle, there's a pinhole. We learned that without changing the wavelength, the wavefronts will continue spreading as if from a point source because they are now practically from this point source. And this is called diffraction. If there are 2 point sources, we learn that we see an interference pattern where we see a maximum, a minimum, and then a maximum, another minimum, and another maximum, and likewise symmetric on the other side. These points are really the centers of these regions. What we actually see would be something like this. A bright region, a dark region, a bright region, a dark region, etc. We learned in the diffraction lesson Huygens principle, which suggests that if there is a gap that is wide enough not to be a point source, it behaves as a series of infinite number of point sources. We are now going to bring these two together. one point source and the other point source. We are now going to open that area completely. So instead of 2 point sources, we now have an infinite number of point sources that are going to form an interference point on the screen. Combining what we know of interference with diffraction, we will see that this gap, behaving as a series of point sources, will cause a central combined constructive interference region on the screen. And there will be an edge, a limit to that constructive interference, which will be the first minimum that is observed on the screen. So it's going to look like this. Let's say the width of this gap is b. The wavelength is lambda as usual, and the distance to the screen will be capital D. On the screen we see a wide central bright region. We call this the central bright region, and the limit, the ending of that central bright region, is our first minimum, the first destructive interference due to all of these point sources that form this gap. So I'll label that as my first minimum. There's another one over here. Please remember from interference lesson that the path difference for the first minimum should be half wavelength. And just like we did for the interference lesson, I'm going to draw lines from the start and end points of this gap, find the path difference at the first minimum, and try to label it on the diagram. This is one path, and this is the other path. Now, since we're looking at the first minimum, which is the first destructive interference, we want to relate the angle that the gap makes with that limit, because we want to make sense of this pattern mathematically. Because we have a full open gap with infinite number of sources, I'm not going to treat this as two sources. I'm going to find the path difference from two rays, one of which is from one edge and the other from actually the midpoint of this gap, to estimate the whole gap. Now the path difference between those two lines should be equal to lambda over 2. Just like we did in the two-source interference lesson, I'm going to draw a perpendicular line from one to the other. See that that's the path difference. That's half of b, and this path difference should be equal to lambda over 2 because we're looking at the first minimum. Labeling that angle over there, writing the sine of this angle, using the small angle approximation that is equal to the angle as opposite over the hypotenuse, which translates into this. And there is our single slit interference pattern formula, which you will find in the data booklet. The angle here is equivalent to this angle right there. So it's very important to recognize the angle on the diagram, because in a minute I'm going to explain the difference of this picture from the one we did for two-source interference, and it's crucial that you see that this angle I'm looking at here is the angle from the midpoint of the gap to the first minimum. Please remember that in two-source interference we used the angle from the midpoint of the two sources. That angle we chose to write our formula was to the first constructive interference. So in this case, this angle goes to the first minimum. Let's see what this looks like on the screen. As you've seen in the demonstrations before, on the screen, you are going to see a white central maximum and the first minimum on either side. Since we are looking at a rectangular slit, not a circular one, the central bright on the screen is going to look like this. And the next constructive interference are going to be symmetrical on two sides, but these are going to be much smaller in terms of intensity. This is brightest at the center, and it gets less bright towards the edges. Zero brightness here, and much less brightness on these next constructive interference points. Let's show how this looks on an intensity diagram. The x-axis is going to be the angle. My y-axis is going to be the intensity I. So at 0 degrees, we are looking at that point. On this diagram, we are looking at that point. This is where the intensity is maximum. And intensity decreases and reaches a point 0, where this is the first destructive interference. So this angle right here is that angle right there. Symmetrically on the opposite side, reaching that point, this diagram is going to have another 0 right there. This angle and that angle are the same. And after this destructive interference, there will be another constructive, which is much less intensity compared to the central max. So this is what we call the central max, brightness maximum in the center, and 0 intensity point, which is our first destructive interference. The angle that extends from the center to that is labeled here on this diagram. Sometimes it's important to mention the wrong way of doing things to prevent some errors from happening. Here is what not to do in a single slit interference pattern intensity diagram. What is wrong with that diagram? Problem is the intensity on both sides must go all the way down to 0. This is the problem right here. This does not go all the way down to 0, so this diagram would not be acceptable. Case number 2. The problem with this one is that the central maximum intensity and the next constructive intensity are too close. The syllabus actually says the next constructive interference in the single slit interference pattern should be maximum 5% of the central maximum intensity. Case number 3. The problem with this one is pretty obvious. It's not symmetrical, and case number 4, this one is missing the symmetry again, so that would be problematic. First case, two-source interference intensity pattern with no diffraction effects. This is an ideal case, which assumes the two sources are point sources with no width at all. If this is the case, then you can draw an intensity pattern which looks like this. As you can see, the intensity of the central maximum and the first maximum and the second maximum, all constructive interference points, are of the same intensity. In this case, the angle from the center of the pattern to the center of the first maximum was the angle that was used to calculate and to derive the formula, which was this. In the single slit interference intensity pattern, the intensity diagram would look like that, where there is a very bright central maximum with intensity highest at the very center of the pattern. The first minimum is where we measure the angle 2, which is given by lambda over b. The angle is not the only difference between these two cases. D is the separation of the two sources. B is the size of the single slit. I'm going to add a third case to this scenario, which we will get back to later. Two-source interference intensity pattern with considering diffraction effects. In the first case, we had 2 point sources. In the second case, we had a single slit. Now in this third case, I'm going to consider two sources which are not narrow enough to be considered as point sources. So they are actually individual single slits, which obviously cause their own diffraction effects. This is one source and this is the other source, which are not point sources. If this is the case, on the screen the intensity pattern looks like this. You can see it's kind of a combination of these first two. A single slit interference pattern has a central bright fringe that is shown as an envelope on this diagram. The interference pattern turns into something similar to the two-source interference pattern, but as you move away from the center, the intensity of each maxima is no longer equal to the intensity of the central maximum, but it decreases and stays within that envelope. And we will get back to this when we learn about multiple slit interference and diffraction grating. This is something we will refer to as Young's experiment in the coming lessons. And we will also look at a virtual experiment which shows us this effect. Okay, now I'm going to ask you to take your calculators out and follow the instructions as I walk through. This simulation shows a gap with the gap size given. It's also given here. The wavelength is given. For red, that's the current screen, 712 nanometers. And we're going to find the angle from the center of the central max, which is 0 degrees, to the center of the first minimum. I'd like you to do that calculation. Once you calculate the angle, you're going to find the angle in radians. Change that angle to degrees and compare that with what is given on this simulation. So let's go. I'm now decreasing the wavelength. I've changed it to 436. Do the calculation yourself and then see if you get the same answer as shown on the screen. Okay, that's it for this lesson. For homework, this is number 1, the second one, the third question, fourth question, part A, and the rest of question 4, question 5, and the rest of question 5. Thank you.